Optimization problems look like what's the lowest cost of whatever scenario? What is the maximum area of a rectangle that can fit inside of an ellipse? What's the minimum distance between thing A and thing B? And the words maximum and minimum aren't always featured. Like I said, lowest cost might be an example, but we're basically looking for probably an absolute maximum or an absolute minimum, which may or may not be a local max or a local min, but if you're thinking about, oh, I'm going to take a derivative and set it equal to 0, you're exactly right. Depending on the situation, you're going to create a model. That model is an equation that describes the situation, and one of the challenges is actually coming up with the equation. Sometimes they're fairly straightforward. Our first example is what's the minimum vertical distance between the parabolas y equals x squared plus 1 and y equals x minus x squared. I generally recommend that if you can draw a picture, if there's a physical situation, that you do. Here we have a picture. It's the graph of two parabolas. One of them is y equals x squared plus 1 and the other is y equals x minus x squared. I'm not using a ruler to measure these things, so a quick sketch is good enough. Y equals x squared plus 1, a parabola that opens up and has a vertex 1 unit up on the y-axis. For y equals x minus x squared, I know I have x-intercepts at 0, 0, and 1, 0 because I could factor out an x. As far as where the vertex is here, if I factor out, say, a negative 1, rearrange the terms so that I end up with y equals negative x squared minus x, then I'm really going to just complete the square inside the parentheses. The linear coefficient is 1, cut that in half, I get 1/2, square that, I get 1/4. So I'm going to add 1/4 inside the parentheses. And then if I look at the negative out front here, I've really added negative 1/2. So to offset that, I've really added negative 1/4. So to offset that, I'm going to add 1/4. If you're not sure about that, just distribute the negative, you'll see it. And then this gives me an equation that looks like y equals negative, whoops, I didn't even write the negative even though I said it, x minus 1/2 the quantity squared plus 1/4, that's in vertex form. So I see that this is a parabola that opens down, but we already knew that because negative x squared here, with a vertex at 1/2, 1/4, and that's what I drew here. All right, so we're looking for the minimum vertical distance. And when I think distance formula. And our distance formula is going to be d equals the square root of x2 minus x1, the quantity squared, plus y2 minus y1, the quantity squared. Fix that square root there. But, I mean, we've got to fix this. We have way too many variables running around. But if I'm going to minimize this thing, I'm going to take a derivative. It's a square root. It's going to use the chain rule. It'll be kind of bad. What I'm going to do instead is use the square of the distance. So uppercase D is equal to x squared minus 1, x2 minus x1, the quantity squared, plus y2 minus y1, the quantity squared. It turns out minimizing the square of a distance gives you the same result as minimizing the distance itself. Basically, that's because if a is bigger than b, then a squared is bigger than b squared. Now, let's look at what it is we're dealing with, the minimum vertical distance. If we look at vertical lines here, or vertical line segments here, between these two parabolas, you can see that some of these vertical lines are shorter than others. And what we're asked for in this exercise is what would be the length of the shortest vertical line. As we know, the distance formula would be the distance between 2 points. And let's say on the upper parabola, we have x1, y1. On the lower parabola, because it's the vertical distance, the x-coordinate is going to be the same. So x1, y2. Our distance formula then, or the square of our distance formula, becomes d is equal to simply y2 minus y1, the quantity squared, because x1 is equal to x2. We're only looking at the vertical distance. We're only looking at the y's. And now, according to the way we've labeled things here, y2 is x minus x squared, and y1 is x squared plus 1. And so we're going to say here that d is equal to x minus x squared minus, I'll distribute the negative here, x squared minus 1, the quantity squared. So d is equal to negative 2x squared plus x minus 1, the quantity squared. And of course, because we're squaring this, it doesn't matter which one we called y2 and which one we called y1. This is our model. And once we've developed a model, then we're usually going to take a derivative, set it equal to 0, and then answer the question using the result. Taking a derivative in this case, d prime, I'm going to use the chain rule, is 2 times negative 2x squared plus x minus 1 times the derivative of the inside function is going to be negative 4x plus 1. Now, if d prime is going to equal 0, then that means that either negative 2x squared plus x minus 1 is equal to 0, or negative 4x plus 1 is equal to 0. So clearly from the second one, we can see that x is equal to 1/4. From the first one, if we just look at the discriminant for the quadratic formula, then b squared minus 4ac is going to equal 1 squared minus 8. That's negative. This actually doesn't give me a real number solution. So the minimum vertical distance occurs when x is equal to 1/4. Now at this point, we got to pay attention to what was being asked. We weren't asked what's the x value for the minimum vertical distance, but we can see it's where the lower parabola has its vertex, right? We were asked for the actual minimum distance. Since we have this expression for the square of the distance, we can say that the actual distance is equal to the absolute value, because we're essentially square rooting a square, right? So the absolute value of negative 2 times 1/4 squared plus 1/4 minus 1, which turns out to be 7/8. And so the minimum vertical distance is 7/8. We can see that that's in the right ballpark there.